Hi, today we're going to demonstrate one use case of the WorkVisualizer, a new performance profiler from NexGen Analytics that provides quick, actionable insights into your HPC application. Let's see how it works. To get started, we'll need data files that hold information about your app. To generate these data files, we use Caliper, a performance analysis library from Lawrence Livermore National Laboratory. For Cocos-based applications, you don't have to make any changes to your source code. Just set up Caliper using the directions in our README, run your app, and we'll handle the rest. The files will be created in the same directory you ran your app from. For this demo, we're using data from a synthetic test case we created with Cabana MD, a molecular dynamics ECP proxy app. Once the files have been processed, the first thing we see is this summary table. This gives us a high-level glance at our app. We can see how many MPI ranks were used, 250, how long the application ran, about a minute, and which call types are present. We can even see which calls took the longest. From here, we can start looking at the visualizations. The proportion analyzer shows us where our app is spending time. Each region of the diagram represents one function. If we mouse over a function, we can see how often this function was called and the amount of time the current rank spent in it. You can tell which rank we're looking at down here. We'll learn more about how to change ranks in a bit. If you click on a function in the proportion analyzer, you can see all of the functions called by that region. If we follow this all the way down the call tree, we can see that this blue function is taking up a lot of time. This is an MPI barrier call. We'll get back to that later. If we want to change ranks, we can use the Settings tab. You can type in any rank you want, or use the arrows to cycle through all available ranks. Once we've determined a representative rank, you can select that here. We'll talk more about the representative rank later. As you can see, every rank has slightly different behavior. The WorkVisualizer can tell you which ranks are interesting to look at. We'll talk about that later too. From the settings page, you can also filter out the depth of visible calls. If you only care about the top-level functions of your main executable, you might want to take the depth down to 1. This is a fairly simple application, so we'll go back to using the full depth for now. The proportion analyzer is helpful for understanding where your app is spending its time. But what if we want to see each individual call over time? That's what the events plot is for. This gives us a trace-like view of every function call over the course of the app's execution. The horizontal lines represent new depth levels in the path, so all of these functions were called by functions up here. You can mouse over functions to see more information about them, and highlighting a function down here will also highlight the parent functions that called down to it. We can zoom around and show the duration of each call. And as before, we can change the current rank from the settings page. We can also filter the depth, same as before. The slicing options are related to our analysis pipeline, which is how we tell you where to look for problems in your app. Let's demonstrate that now. Our analysis accomplishes two things. First, we're going to find a representative rank. This is the rank that exhibits the most common behavior among all of the other ranks. Once we've determined this representative rank, we're going to divide its execution into repetitive slices. The idea here is that if your program has a solving loop or some other iterative process, we want to identify each repetition and figure out if any iterations are running slower or faster than normal. Looks like our analysis has finished running. Right away, we can see that there's something we can improve. 4 ranks are losing time. Lost time is our metric for finding potential issues in your app. The idea is that if the representative rank has to wait for another rank to enter an MPI collective call, then time is being lost. In an ideal, balanced app, every rank should reach the collective call at the same time. So, if we're losing time on 4 ranks, we want to figure out why. To help with this, we can use the analysis viewer. These plots are showing us the results of the analysis pipeline. We can see the slices that we found, along with the average time lost across all ranks on those slices. Obviously, something's going on with slice 3. Down here, we can see which ranks are causing problems. Looks like rank 4 has the most time lost, followed by these other 3. This is a pretty dramatic test case. For a more subtle problem, we might want to view one slice at a time. Now, we can drag through the slices that lost the most time. And here's slice 3. Looks like something's definitely going wrong here. Rank 4 is losing 90% of the total program runtime. At this point, we know which function is taking the most time, as well as which rank and which slice is losing time. It's time to take a look at the code of our synthetic test case and see if we can find the problem. The WorkVisualizer pointed us to the artificial performance problem in the modified code. Removing this leads to improved program execution. If we rerun the updated app, we can see that the time loss is negligible, the ranks and slices are well balanced, and as a result, the total program runtime has been greatly reduced. This was only one use case of the WorkVisualizer. With more features than we could show here, and plenty of ideas for new ones, we hope the WorkVisualizer will become a valuable tool for high-performance computing, performance profiling. The WorkVisualizer is open source and can be installed for free from GitHub. Finally, you can always reach out to our developer team with questions, comments, or suggestions at info@ng-analytics.com. Thank you very much.